Okay, so this is a bonus because a lot of people ask me about what are these Navier-Stokes equations that I said that came from an assumption on that stress tensor. So call that, right, for all fluid analysis, you just draw, you always draw a box of fluid, right? And we have these body forces, it's called body forces, that just act on a center of mass point. So this could be from all sides like this. And then again, we had these surface forces. So the surface forces being, if I consider some fluid element, there are forces, something like we draw this box, and we call those shear forces, and these are pressure terms or normal forces. And you had that 9-term Cauchy stress tensor that is just describing all 9 components of forces that could happen on some element, right? I mean, this is really some cube that you have, right? So there's a whole bunch of stuff you describe from just that 9-term stress tensor. So I had in the notes that one assumption that you make on describing these forces is a Newtonian fluid. One of these surface forces has this relationship, right? And this is a shear force. So for Newtonian fluids, this number is a constant. So there's a force associated with resisting with this element of fluid not wanting to be like this. It doesn't want to shear. And that force is, right, for a Newtonian fluid is modeled like this, where this is a gradient of velocity. So right here and right here. So this change in velocity, linear proportional to this gives you a viscous force. Okay, so if you make those assumptions on that Cauchy stress tensor, where you have like this XX term, you say that all the normal forces, right, you can relate them to a velocity. After you plug all that stuff into that Cauchy stress tensor, and you use for incompressible, you have to use this. Remember, for continuity, we're saying this for an incompressible liquid, the gradient operator. If you use that and then you make those substitutions, you write out the Navier-Stokes equations for viscous fluids. And those are, I'll use U, everyone uses U. So unsteady term. And then we have, so this is just that material derivative term we have. You have this is equal to the negative pressure, so the negative gradient of your pressure field, and then a viscous term. And for compressible, there's another term that's zeroed out because of this relation, because of continuity. So this is just the end-all be-all of all fluid equations that we have, Navier-Stokes equations for incompressible Newtonian liquids. If it's compressible, there's another term, but I mean, we're going to look at compressible effects way later. So these are really this is the Navier-Stokes equations. All fluid problems, right, come from this equation. All fluid problems, you can begin by writing this thing down, cutting terms away, and then making an expression. So in the next lecture, we will do a pipe flow example where we will solve for a velocity profile, but we're not actually going to do it from the Navier-Stokes. You can do that, and if you go into more advanced classes, you start from this, make assumptions, cut terms away, and then get the solution we will get in the next lecture. But we don't have to do that. We can think about it more in just a force balance. But those are the Navier-Stokes equations. They come from an assumption on that Cauchy stress tensor, and I think I had that up there. Remember this 9-component thing? So you make the Newtonian assumptions on these guys right here, and then other things, and then on the shears as well. After you make those assumptions, you can write it in vector format like this. Understand this is a gradient operator, right? So this is describing 3 equations. So in total, there are 27 terms to. If you write out every single component, there's 27 terms involved in this giant thing. But I like the vector format because you can kind of rationalize the expressions a lot more. And just the classic rationale that we always have for this is, I'm sorry, I should have a density there. That's a mass. So you have that this part is the inertial forces of a fluid moving. Let's draw this little cube. Right? So there's forces. There's inertial force terms, then there are these pressure. Right? And then you have the pressure field. So these are great. So this term is a pressure term that's involved in your velocity field. When you have that body of liquid, there's a pressure at every single point in that field. Gradients in those pressures create a force. So that's right. This is the pressure term. And then the viscous force is talking about curvature of velocity profiles. So that's where this realizes a double derivative right there. And that comes from the substitution of that stress tensor. And these are the main terms. What happens commonly is you can just say some of these terms matter and some of them don't matter. That's exactly what the Reynolds number does, actually. Remember, so you have a Reynolds number. Right, so this is a Reynolds number. And you get this Reynolds number by scaling this equation, and you'll see that there's a term that pops up. I don't want to do that right now, but that's just where it's coming from. So for Reynolds numbers that are very, very small, essentially, let's say even like much less than 1, this side matters most. So it's a balance between your pressure and the viscous forces. So that's for low Reynolds numbers. The other case is if it's for Reynolds numbers that are extremely high, technically much greater than 1, it's a balance between these 2 terms. It's a balance between the pressure gradients of the normal forces and your inertial forces. So very fast fluids have a lot of inertia, and that must be balanced by the pressure gradient, and it's measured with that Reynolds number. So, right. So right, you kind of right. So this balance of terms, which is what we'll have a lot of pipe flow involved with, is a low Reynolds numbers. High Reynolds numbers describe turbulent flows. But those are the Navier-Stokes. You don't really have to be experts at them in this class because we're not going to start from this giant set of equations and work our way into more specific problems. But a lot of people wondered what I was talking about, and that's what they are. And all fluids must obey this equation to such that we know of. We don't know of any fluids that don't obey this. Non-Newtonian fluids, right? For a non-Newtonian fluid, that means that this is not a constant, but is some function of the velocity. But you can still write it out, and there's another extra term that comes in from there. Just everyone wanted to know, so that's my little word about what the Navier-Stokes equations are. You don't have to be experts at it in this class. We're just going to do pipe flow problems. But I'll mention it again since you know what it is now later.